Thank you all for attending my talk. It's Ian mentioned, we just met now. My talk's entitled Controlled Waveform Low Heat Input GMA for Reduced Distortion in Shipbuilding. And I'd like to acknowledge NSRP for sponsoring this work, and also Gene Frankie, who's my co-author, who's now sitting in the audience. And I work for the Naval Surface Warfare Center Carter Rock Division in West Bethesda, Maryland. So if you have any questions, you can come find me afterwards or ask in the session. So the overall objective of this work was to look at the new generation of controlled waveform technologies that have been developed as a replacement for conventional short arc. And the idea is that you can combine the benefits of short arc welding and hopefully eliminate some of the potential drawbacks that are typically associated with short arc. So namely, you can get sound welds at lower heat inputs, which allows you to produce smaller weld sizes and therefore reduce distortion. And as part of this work, we looked at three potential variants of the controlled waveform technology. You have STT from Lincoln, which is surface tension transfer, cold metal transfer from Fronius, and then regulated metal deposition from Miller. And I'm going to go through a little bit about each of those. This is the Lincoln power supply that we looked at. It's a PowerWave S500. You can see there's an S500 module here. That's the main power supply, and then the STT module is an add-on. You have a pretty standard GMA welding torch. You can probably see here too, there's a dual wire feeder, dual torches. This is a pretty large system, and it has the STT again is a separate module. So for the STT technology, this is courtesy of the Lincoln website. Basically, there's a background current that helps form the droplet. You get a brief short down here, and then a pinch current and a peak current help to detach the droplet, form that pinch, and then to reignite the arc. And then finally, it trails out, and everything restarts again to continue the weld. Now, for the Fronius variant, we're looking at a CMT 2700. This is a suitcase style, so it's an integrated wire feeder, and the CMT capabilities are integrated instead of having a separate module. The thing that's unique about the Fronius variant is this mechanical component here, where there's a mechanical buffer, and there's actually a little actuator inside of there that helps to take up slack in the wire as the wire is reversed during the process, and a push-pull style gun. So that there's a mechanical component added that Fronius will tell you adds a layer of performance to it, but from a use standpoint, it's a little bit more cumbersome setup for the welder in using the system. You got a similar type of idea here. The thing that's unique is the mechanical component. So you have the wire moving towards the work. You have the arc established. Eventually you get your short here. The wire starts to retract. That helps to produce detachment. And then again at the end you have the wire reversing directions, heading towards the work again, and reestablishing the arc. And so that's the uniqueness of the CMT system from Fronius. Then finally, our third candidate is Miller, which is regulated metal deposition. We have an Access 300 power supply. It's a pretty standard type of system here. You can see the wire feeders up here, integrated RMD technology, and again, it's a pretty standard GMA welding torch. So here's the RMD schematics, courtesy of Miller. So you get a background current that helps you form your droplet. You get a wetting where you have your short, and you get a pinch and a clear that helps you to pinch down the arc and detach the droplet. And then finally, you get your blink and your ball, which really are the peak current again that helps to restart the process and form a new ball for detachment as the process continues. One thing I did want to mention is that all three of these technologies are synergic in the fact that they sense and adapt and try to maintain consistent arc behavior throughout the weld, even if it's a manual process. So this work was conducted in two stages. You have part one's preliminary investigation, where we wanted to get our hands dirty and try to performed some preliminary experiments to guide the second part of the work. So as part of this, what we knew going in was that typically these technologies, STT, RMD, and CMT, are best suited for really thin materials, open root welds, and for filling gaps. And what we proposed to do to try to take advantage of those things would be to do a T and a single V weld using 1/4 inch thick DH36 and a 3/16 root opening. So that's kind of pushing the limits for the thickness and the type of material that really are in the wheelhouse for this, but we wanted to try to make it as applicable as we could to something that would benefit a shipyard. So we ran that by the power supply people that were helping us out and the shipyard partners, and that's what we went with after we got agreement from everyone. So here's the matrix that we produced for the preliminary investigation. The important thing here is that there's a T-weld and a butt weld using Lincoln STT, T-weld and a butt weld for Fronius, and then a T-weld and a butt weld for Miller. And we used 045 ER70S6 wire, DH36 plate, C5 shielding gas, and everything was done in the vertical down position. And one other thing that we added to be another degree of difficulty was that these welds were actually performed by shipyard welders who were visiting NSWCCD. So they had limited time to get their hands on the equipment and optimize their technique. And we think that's part of the reason why you see the notes here that the T-welds typically exhibited fusion line defects, and there were concavity and convexity issues in some of the butt welds. But they weren't really major things that couldn't be corrected in the second part of the investigation. So now we're looking at the T-weld macros, and here these are the defects that I was referring to. All three of these welds contain those. And really, we think that was just a function of the parameters and the technique not being optimized. In the second part of the investigation, you'll see that I think we were able to clean those up. In the butt weld macros, you can see, we got the Lincoln, Fronius, and Miller. And these are the convexity and concavity issues that I was referring to. You can see the root down here, you got a significant concavity issue. And then some of these crowns are excessively convex. So definitely needed additional parameter optimization in the second half. And because of some of the defects that we found, we realized that it was important to do, but we knew that we needed to do some volumetric inspection to ensure that we were actually producing sound welds. One other thing we did for this set of welds is micro hardness traces. So what you're looking at is Vickers micro hardness as a function of distance, and we're going from the root to the crown for each of the three processes. And really, there was no significant difference between the observed hardness for each of those three power supplies. You have the typical scatter that you can see with micro hardness, but in general, there was no real trend to be determined from that. So now, with the information we gathered from part one, we went to our shipyard partners and said, here's what we found, and here's what we'd like to do moving forward, and we had a discussion. And so one thing there are a couple things that came out of that. The first being that the use of a T-joint wasn't really desired by the shipyard partners. They typically would attach their stiffeners using fillet welds with no appreciable gap. So we've switched from using the T-joint configuration to the fillet configuration. This is kind of a difficult thing to move towards with these processes, because that open root is something that helps these processes, or that you can really take advantage of with these processes. But that's the direction we moved for part two. And then one other thing that we changed after part one was originally we wanted to do this such that you'd use the controlled waveform process in the root and then switch to a more conventional pulse style or pulse process for the fill passes. But it was determined by the shipyards that they didn't really like the idea of switching back and forth between the two processes. So we decided just to stick with the single controlled waveform process for both the root and fill. All right, so here's the experimental matrix for part two. What you can see is that we have two baselines here. There's a conventional short arc baseline for the butt and the fillet. There's a pulsed GMAW baseline for the butt and the fillet weld. And then here you have the STT, RMD, and CMT all have a button to fillet weld. And then there's a combo process down here. So the root there was made with an STT process, and the fill pass was made using pulsed GMAW. Again, it's or the other parameters that are important here: the O35 ER70S6 filler, DH36 base plate, and we switched to a C25 shielding gas at the request of the shipyard partners. And then one other thing I wanted to point out here is that duplicates of 5, 7, and 9. So these are the butt welds made using the controlled short arc processes, or I'm sorry, the controlled waveform processes. We had a second welder produce those welds just to see what the difference would be based on welder technique, welder experience. And so there's duplicates of each of those welds. And here are the configurations that we used. There's the butt weld had the 3/16 root opening. It's the 1/4-inch thickness, and it was filled up in 2 passes. The fillet weld, again, 1/4-inch thick DH36, and it was filled up with 3 passes, or made using 3 passes, and there was no appreciable gap in the root. So here are the butt welding parameters. So again, this just the butt welds here. You have conventional short arc, pulse GMA, STT, CMT, RMD, and the combo. And the parameters are generally fairly similar, but the important thing to note here is the average heat inputs that were produced. So you can see the highest heat input of these processes was the pulse GMA. The lowest heat input was the conventional short arc, and then the controlled waveform processes fell in the middle, and that's generally what we anticipated. So you'd see there's very little difference between the controlled waveform processes. And now for the second welder, one thing that was a little bit different was that welder 2 had previously had experience using these controlled waveform low heat input processes, and so he was actually able to reproduce the parameters in terms of amperage and voltage, but weld at a much higher travel speed. And that's what led to these lower heat inputs that you can see in the column here. So compared to in the area of 21 to 25 kilojoules for welder 1, welder 2 was actually able to produce welds at around 8 kilojoules per inch. So pretty significant difference. I apologize for the missing data here, but we weren't actually able to hook up our external arc data monitoring system because of the style of the power supply. We'd actually have to remove the board to get our sensors in there, and because the system was on loan, we didn't really want to go down that route. So again, the welder 2 was actually able to produce much lower heat inputs, and that was because of his previous experience using these types of systems. So now I'm just displaying the heat input graphically here. Again, conventional short arc had the lowest heat input. Pulse GMA had the highest heat input, and the controlled waveform and combination processes fell in the middle. And then for welder 2, the heat inputs were actually much lower based on the higher travel speed that he was able to weld with. And the important key is, obviously, heat input's important, but we wanted to see how that affected distortion. And as you'd expect, the trend for heat input matched well with the distortion trend. So the lowest heat input was the conventional short arc, and that's what exhibited the lowest maximum distortion. Pulse GMA had the highest heat input and also exhibited the highest distortion. And then again, the conventional or controlled waveform processes fell in the middle. All of these welds were ultrasonically tested in accordance with the Navy standard Tech Pub 271. The acceptance criteria was MIL standard 2035A Class 1. And in general, all the welds were sound with the exception of the weld made by welder 1 using CMT. There were 2 small rejectable indications, but we don't feel that was a result of the process. It was more likely due to workmanship. And the fillet welds did not receive UT. So now here are the macros that we were able to produce using these processes. in general, like I mentioned before, the parameter optimization and general comfort level with the systems, we were able to achieve, I'll say, much better looking welds. The convexity and concavity issues aren't really as significant. The defects that were there originally aren't really there anymore. But one interesting thing to note is that, in general, the welds look pretty similar with the exception of the root pass. So the pulse GMA, you're actually able to achieve pretty flat backside. And the STT root passes, you're actually able to get a convex backside. But for conventional short arc, CMT, and RMD, it's actually concave on the back. So that was one difference between these. But in general, pretty similar bead profiles. Now for welder 2, again, the STT is a pretty flat backside, whereas the CMT and RMT have a convex backside. And it's kind of difficult to tell with the macros on 2 different slides here, but the bead profiles are a little bit different between welder 1 and welder 2. But that was most likely due to the nature of the grinding between the 2 welders. Welder 1 used a relatively light grind, whereas welder 2 was a little bit more aggressive in his initial grind. Therefore, the bead profiles are actually spatially a little bit different in the depth of the weld. But in general, everything's pretty similar between the butt welds of welder 1 and welder 2. So now moving on to the fillet weld parameters. Again, there's a short arc, pulse GMA, STT, CMT, and RMD weld for each of these, for each fillet weld. This time, the welding parameters and average heat input didn't really track as well as we would have expected or anticipated. You can see the conventional short arc doesn't actually have the lowest heat input this time. That's actually the CMT weld had the lowest. And some of these controlled waveform processes actually have heat inputs that are pretty close to the pulse GMA. So in general, everything fell between 18 and 28 kilojoules. The heat inputs are pretty uniform across. And again, showing this graphically, you can see that trend that we had for the butt welds, it doesn't really track for the fillet welds. Pulse GMA had the highest heat input, but that was the only thing that really carried over from the butt weld heat input data. Now, here are the fillet weld macros. You can see, in general, for all 5 of these, they're pretty similar bead profiles. You do get minimal penetration into the weld and or into the webs and flanges, and that's pretty consistent for all 5 processes. And then also, there's very little penetration between the web and the flange. But the important thing is that visually, everything's pretty similar between these processes. So it's not like we're seeing significantly reduced penetration based on the controlled waveform low heat input processes. So in summary, we have a series of butt welds made using short arc, pulse GMA, STT, RMD, and CMT. We had a second welder produce a second set of butt welds using the controlled waveform processes. Welder 1, welder 1, pulse GMA had the highest heat input, short arc had the lowest heat input, and the controlled waveform processes generally fell in the middle. As expected, the distortion measurements tracked well with those heat input results. Welder 2, he had previous experience using these processes, therefore he was able to travel faster and achieve much lower heat inputs. And there were only minor convexity and concavity issues observed, and in general, everything passed Class 1 except for one CMT butt weld. So for the series of fillet welds, pulse GMA, STT, RMD, and CMT, heat inputs were pretty consistent across the 5 processes. The bead profiles and the penetration was pretty consistent, but pretty minimal at the intersection between the webs and flanges. But overall, in general, I think these processes do show promise. I believe that they are capable of producing sound welds at lower heat inputs, which would result in lower distortion. But the nature of manual processes, I don't really think you can take full advantage of that, especially given the thickness of materials and the joint configurations that we were using here. So in slightly different cases or through mechanization, you could really further improve on the benefits of these machines. So again, I'd like to acknowledge NSRP, collaborators Ingalls Shipbuilding, and power supply manufacturers Lincoln, Fronius, and Miller for providing the power supplies for this investigation. And if there are any questions, I'd be happy to answer them.
Thank you, Jeff. So we do have 8-9 minutes for questions. So, yes.
Sure.
I think it's really nice to see work done on the shop, because show us how we do this to work outside the laboratory. So I'd like to congratulate you for the work. We also experiment some concavity in the root when we weld with that parameter, especially because you weld it downhill, right? So
yep.
In our case, we switch by the U joint, U configuration, so we saw it that way. But my question is, how downhill position is important in a shipyard? Because I think it's more like flat or horizontal. Is because of some need, or also, if I'll be the second question, is concavity important inside that new specification? Because I don't know that standard.
So the first question.
Why downhill?
Downhill, and we have a bunch of people from the Navy here that have more experience than me that will be able to help if I get this wrong. But typically, downhill isn't something that you'd want to do in a shipyard. It's probably actually against the rules to do downhill welding. The reason that we did it for this particular case was that that's one of the things the power supply manufacturers suggested that we do. It actually helps with this process, so that the open root or having a root welding downhill are some of the things that help these processes perform better. And I guess I shouldn't say that across all three of the variants, but a couple of the people that helped us optimize parameters initially said that we can get better performance welding downhill. But in general, that was a compromise, not really something that we'd want to do for shipbuilding applications. And
you also might want to add, Jeff, that vertical position is very important in the Navy. It's just downhill progression.
Right.
In the vertical position is not something that we do. We generally do uphill. But Jeff explained why we did downhill for this particular.
And then could you remind me the second part?
Oh, yes. I forgot, sorry.
Perfect. Actually, maybe Ashley can help me. She knows all the NDE specifications. But my understanding is that you wouldn't want that. That might be a visually rejectable feature.
Having it's pretty much underfill on the root side, and it actually takes away from integrity of the actual strength of the plate, because the ideal is to have the weld be just as much thickness as the base plate. So that's why there's tolerances in place for concavity and convexity. You can't have too much, and you can't have too little at the joint, because that actually will weaken the joint.
Right, but there's no tolerance against that.
There's tolerance.
Yeah. So one of the things I mentioned was for the. Yeah, one of the things I mentioned for UT was a Mill Standard 2035A acceptance criteria. There would be similar criteria for a visual inspection, and that's probably where that information will be found, what the maximum convexity, maximum concavity, and what the rejectable indications would be for your particular application.
I think for the numbers for concavity, I think it's a 16th. You can't have more than a 16th. And for convexity, I think it's 3/32.
Hi.
First of all, can we say in that case the political material is not so suitable for TNT or similar waveforms? But as far as I heard, that there are some other, machine producers who are, for example, producing very good, penetration in especially in fillet valves. I'm not so aware about the heat input, but it's very possible, as far as I know, it's possible to, valve travel speed can be more higher, and then heat input can be decreased in that case.
Mhm.
Maybe if you can check about, it would be helpful for your study for future.
Yeah. And one other thing that some of them are doing is integrating the controlled waveform nature of it with something else. So, for instance, Fronius has something they call CMT plus pulse, or I think I have the name right. But what that does is, there's 2 cycles of CMT and then a cycle of pulse, or some combination of those. And what that's designed to do is help you achieve those benefits and push towards higher thicknesses. So that's one way that they might be able to push into.
Problem. As far as I know, the company, the machine producer Lodge has that such options.
Okay.
I don't know the exact mechanism of waveform, but as far as I know, they can succeed, high speeds, root valves with a very high penetration.
Okay.
You mentioned the processes were synergic.
Mhm.
So what variables are they measuring, and what variables do they change with that, within those processes?
That's something that's a difficult question to answer. I think we stand around in the lab sometimes and try to wrap our minds around what exactly is fixed and what exactly is changing. I think the correct answer is probably it depends on which manufacturer and which variant you're talking about. And I assume you're asking because it's a concern to, yeah. And one of the things that a lot of the companies are doing now is that you can actually bracket how much play the system has. So you won't know, unless you're actually capturing the waveform or recording at a high rate, you wouldn't know exactly what it's doing, but you can set limits on how much variance it has. So if your concern is that you don't want to go outside of this current range, this heat input range, if you're trying to adhere to a procedure specification or something like that, you can set limits on a lot of those. But as far as answering exactly what it's doing at any given time, that's kind of a challenge unless you're willing to collect all that data. I'm sorry, that's a non-answer, but it's, yeah.
Okay. That's about all the time we have for questions, so I thank Jeff again. Thank you, Jeff.
Thank you.